let's talk about vector dot product, also known as scalar product. We'll start with what's more familiar, which is the simple single coordinate frame case. And what I mean by a single coordinate frame is you're probably familiar with seeing a set of axes like this. This is a 3D coordinate frame. And so we know that these are each unit length and that they're orthogonal to each other, which means that they're perpendicular or 90 degrees to each other. And I could have two arbitrary 3D vectors. We'll call this one U, and we'll call this one W. Let's define U in terms of some arbitrary variables. So we could say A in the I hat direction plus B in the J hat direction plus C in the K hat direction. Similarly, we could define W. Let's use different arbitrary variables, X in the I hat direction plus Y in the J hat direction plus Z in the K hat direction. And you may have seen vectors also written in column matrix form, which is sometimes convenient. So you might have seen something like this, where we just write the coefficients. And really what we're implying is that these are just the coefficients A, B, C, but that they correspond to the I hat, J hat, and K hat components of this vector. So if we wanted to compute the dot product of U and W, you've probably learned that you can just multiply the components together. So the I hat components are A and X, and then we add the J hat components, B times Y, and the K hat components, C times Z. And this is true, but it sort of hides something that's going on. Really what we're doing is taking the dot product of all components of U with all components of W. And so let's write that out explicitly and see what it looks like. So here we have U dot W in explicit terms. So what you should realize is that the dot product is just like multiplication when it comes to expanding these terms. So we can write them all out. First we'll do this term A I hat dotted with each of these. So we have A I hat dot X I hat plus A I hat dot Y J hat. It can be useful to rewrite this with all the scalars drawn out in front. So if we do that, it looks like this: AX times I hat dot I hat plus AY times I hat dot J hat, and so on. And now you may recall that if we have orthogonal unit vectors like I, J, and K, then we have the property that K hat equals 1. But all the others, for example, I hat dot J hat, that equals 0. And the reason is because if we go back to the core definition of the dot product, if we have I hat dot J hat, it's the magnitude of I times the magnitude of J times the cosine of the angle between them, which I'll denote theta ij like that. So the magnitude of I is 1 and the magnitude of J is 1. And the angle between I and J over here we already said is exactly 90 degrees because these are orthogonal unit vectors. So if the angle is 90 degrees, then cosine of 90 gives us 0. So even though this is 1 and 1, we get 0. Whereas I dot I, we have magnitudes of 1 and cosine of 0, which gives us 1. So by remembering this, we come down here and say, great, a lot of these simplify. So this becomes 1, this becomes 0, this becomes 0, this becomes 0. I notice there's a small typo here. This should be a plus sign. And of course the result is what we had in the first place, which is AX plus BY plus CZ. So you may be wondering where I'm going with this. And the answer comes when we have a more complicated system with more than one coordinate frame. So now let's do this where we have two coordinate frames. We'll have frame A, and we'll label its unit vectors as AX, AY, and AZ. We'll have another frame, which we'll call B, which could be rotated in some arbitrary sense, and we'll label its unit vectors BX, BY, and BZ. So let's go ahead and use the vectors U and W again. So here we have U, which is described in terms of the A coordinate frame. So we have x1 AX plus y1 AY plus z1az. We have w, which is described in terms of the b coordinate frame. So we have x2bx plus y2by plus z2bz. And we'll do what we did before and write these in column matrix form. But you might start to wonder something, which is, wait a minute, these coefficients describe A-frame coordinates, and these coefficients describe B-frame coordinates. So, does this work? Let's come back to that. In the meantime, let's use the definition we know to compute u dot w. If the way you remember dot product is that it's simply the sum of the product of components, then you might naively think, okay, this is x1, x2 plus y1, y2 plus z1, z2. The problem here, of course, is that you've implicitly assumed that ax and bx are parallel unit vectors. So let's write it out like we did in the previous case explicitly. And now we'll expand out this dot product. So here we have fully expanded all the terms in this dot product. So we have x1, x2 times ax dot bx, etc. What you might realize is that there is no way to simplify any of these dot products without more information. Here all I've told you is that we have two arbitrary frames a and b with some rotation between them. So we don't know the dot product between ax and bx, or ay and bx, or any of these other products. In a later section, we will talk about rotation matrices. And as a preview, the key is that all of these dot product terms are actually the components of the rotation matrix that relates frame A and frame B. So the takeaway is that without any more information, this is as far as we can get on the dot product. And this original solution that we got using a simple definition of the dot product really is completely false. So in this class, when you are asked to take the dot product of two vectors, you should write it out explicitly in this form, and then do any necessary expansion to get their appropriate terms. So finally, we come back over here to these column matrix representations. As we've seen, we really shouldn't just write these vectors as column matrices without some indication of what coordinate frame they're described in. So if we do want to do this, we could say that this vector is x1, y1, z1 described in ax, y, z. And similarly, that this vector w is x2, y2, z2 in b, x, y, z. The a makes it explicit that this vector is in coordinate frame A, and the x, y, z makes it explicit that these coefficients are actually in that order. You can imagine if these were numbers, it wouldn't be clear if it was just like 1, 2, 5. It wouldn't be clear which one belonged to x, y, or z.